Hello there. In this presentation, I will show the paper QAOA for MaxCat requires hundreds of qubits for quantum speedup. This paper was published in 2019 and deals with producing a forecast in order to answer the question, when will QAOA be competitive against classical algorithms for optimization tasks? This is a possible circuit. It is composed by two parts. There are these gates called EU that should enable us to perform arbitrary transformation to the qubits, which we can think of as arbitrary rotations in the block sphere. And then there are these C0 gates that enable us to entangle all the qubits with each other in a very specific way. Finally, I have drawn here Schrodinger's cat in order to remind us that the results are probabilistic. Again, Schrodinger's cat, and below him, Erwin Schrödinger. And again, this idea of a circuit, applied in this case to only one qubit, being an operation that transforms its state. In particular, visualizing the block sphere, it changes it, it rotates it, no? It changes from one certain point, here in blue, to another point, pointed by the arrow in green, okay? So we could think of this circuit as just a black box which has knobs, and each knob enables us to twitch a certain parameter. So if we wanted to build the most general one qubit state, we would only require one parameter, here alpha, because of the normalization. If we would require the most general m qubit product state, then we would require actually m parameters. Here incorrectly symbolized by the same alpha for each, but it's not the case. So the optimization problem called MaxCat, the way to maximally partition the graph in two parts, is solvable in this framework by noting that the following scalar function, which in physics is called the Hamiltonian for the problem of Ising, where the coupling between the elements is not now agreed, but the adjacency matrix of these graphs is actually minimized by the MaxCat solution. It's worth noting that actually the global solution for MaxCat is degenerated, as actually they could belong to, the groups could be actually inverted, and it is this degeneration which in the encoding, in the quantum encoding of the optimal state is produces actually not a product state but an entangled state. For example, 50% 000 and 50% 111, which is not a MaxCat solution, but it is an example of entanglement by degeneration of their value. So moving on, actually trying to minimize this functional pressure by changing the final wave function state can be done using actually a quantum circuit coupled to a classically controlled loop that is controlled by an optimization algorithm. Here in the previous example, it was the hand moving the knob. Okay, so this is what the authors of the paper do in order to produce a simulation, a classical simulation, and in order to produce a forecast. So they used Intel Corporation's QHipster quantum simulator, which is a noiseless simulator, and then they used it to produce to make the following operations. First, they generated the problem instance. They only consider 3 regular graphs, which are, for example, for the case of 4 nodes in B and 8 nodes in A, graphs where each node has rank 3. Then they produce the gate decomposition, for example, in the problems we saw in class at Paris-Saclay University with Benoit Valiron. For example, Qiskit or Qiskit, which is a Python simulator. mentions in its documentation that IBM's implementation of the most arbitrary U operator in the Euler-Angle formulation is actually implemented using only fixed rotations in the x dimension and variable rotations in the z dimension. So we note this is equivalent to this. Authors also produced a schedule compatible with the hardware, not their hardware, but actually the hypothetical hardware where the quantum circuit would run in this competitive future. So in order to produce the schedule, they used another paper by Intel Corporation, which grabs the quantum algorithm and the gate sets decomposition and produces actually the quantum circuit. It colors it according to their commutation relationships and produces the logical data precedence graph. The hardware connectivity enables them to produce an NP-hard problem, which is the schedule itself, where in this paper by Intel Corporation it is proposed that an ad hoc strategy to solve it approximately. The underlying qubit connectivity in this paper, not the Intel Corporation, the one we're focused on, is a grid. So here it is an example of 3 steps for the schedule for the grid the authors used. We're noting here that there were actually only 8 qubits. This is the case for the 8-node graph, and they solved it with 8 qubits. They did not use ancilla bits in the scheduling, which was a design decision. Anyway, here the colors of the schedule do not correspond to the colors of the implementation proposed in Intel Corporation's paper, but just shown in blue actual quantum gates and in green swap operations. Later on, the author's figure, the one we are looking at, shows here in the red square that they computed the quality of the approximate solution. They actually computed an approximation of the metric quality of approximate solution. So they were only computing one of these points in every lap, just watching how it goes up or down in this plot. Could be interpreted as the probability of recovering the actual global solution for each of the number of qubits, independence of the actual circuit's depth. The also called variational hyperparameter, also called step, and symbolized by the letter P. Here in green, P equal to 8, and in red, P equal to 4. Then they produced the actual core of the simulation. They do not only integrated they did not only solve the linear system for all the gates, but they also introduced noise gates. That is a central part of my written work, which is available in this video's comments. So here they noted that there require approximately 400 noise realizations, 384, in order to produce stable samples, in the sense that once you commit yourself to some level of noise gate parameterization based on empirical values measured in different laboratories, as it's mentioned in the paper, here 500 for example 500 microseconds for the decoherence time, so which I'm not sure that's realistic, but anyway it's an example. So for different instances of one same noise gate, the number of noise realizations was required to be at least of some level high in order to make it robust. The idea underlying this concept is the statistical concept of actually referring to the expected value by measuring the sample mean. Anyway, so they took 1,000 samples in order to compute. Again, the same concept is in play here, the empirical mean, in order to know, because we mentioned earlier that the results are probabilistic, And finally, based on this result, yes, the computed distribution, they optimize the parameters in order to keep minimizing the scalar function, here the Hamiltonian of the associated Ising system. Okay, this is not a figure from the graph, just random Google image for simplex minimization. Anyway, so actually the loop would continue in the so-called variational iteration. It would be a variable number. The most general case would be a variable number of iterations where the step size is also variable, no? But this was not the case for the authors. They just fixed the step size at 4 and 8, as we will see later. 4 was one instance and 8 was another run. And just the variational iterations was fixed at 20 loops, 20 circles through the loop. So let's go to the results before we spend more time. Trying to be brief, I just want to show that these are not the computational time measured in QHipster, but just the time it would take in a real quantum circuit implementation, no, in a quantum circuit implemented in a quantum system, where they used some model for time that includes the common Aronson claims, such as the time required for measurement, the time required for state preparation. So under this linear model of time, they produced then the following estimations, and as can always be done, they fitted these points with a straight line that is actually an exponential with a small exponential coefficient. So this seems this may be questionable, no? Because how would we know that this is an exponential model? Their claim is that the quantum implementation is still inside the exponential time complexity class, which is not obvious from this drawing as it could be linear, but anyway. So they fitted the exponential function. They did not mention it was this exact function. No, I just proposed the offset, but they mentioned that exponential model, yes. And well, they measured these parameters for the exponential coefficient, which differ between each other by approximately 10%. They also measured the time taken by the classical state-of-the-art solver, for which they used ACMAX-SAT. And also they fitted the exponential function, which here it is clear now because it's a logarithmic vertical scale. Also under the hypothesis that there is this asymptotic regime and we should only pay attention to that regime, which is correct. Anyway, so when they plot both results together and they project the exponential estimation over the quantum estimation of time using the 95% confidence bands, which can be computed from the goodness of fit, for example, R-squared metric, they arrive to this drawing, which they use to answer. This is not their graph, it's my own graph, which is just used to answer when will these lines cross each other, when will the quantum implementation will be more efficient than the classical solvers. They say several hundred qubits will be required. I just added a few thousand because it seems not very robust. And also, it was their observation, which I here give space to, the fact that when the step size changes, the variational hyperparameter, the depth of the circuit, then the exponential factor, I mean, here there were only two samples, p equal to 4 and p equal to 8, and the exponential factor differed by 10%. So their question was, if the exponential factor keeps increasing while we increase the step size, which is on the other hand something expected in the community agreement is that the step size should increase approximately logarithmically with the number of qubits, here called also binary variables, to settle the issue of are actually the number of nodes in the graph equal to the number of qubits, or will we use ancilla bits? But leaving that discussion aside, which is something I just bring up in order to show the complexity of the problem, actually to increase the complexity of the analysis, we could address the author's observation that actually a further work could be just these results we are looking at here should have a third axis that goes inside the screen, just to show actually the quality of the approximate solution in order to consider the picture entirely, no? In order to incorporate correctly the fact that yes, the forecast could produce a higher number of required qubits if we consider variable step size, but that should inevitably include the analysis of the incorporation of a quantitative incorporation of the approximate, the goodness of the approximation. So leaving that aside, we just visit the author's comments and conclusions, which are first, that QAOA will be time competitive with approximately 1,000 qubits. It was for the case of MaxCat in 3 general graphs and using simplex optimization, do not forget that. And then I just add here, it may take even longer, which is what they mentioned about the exponential factor, if it keeps increasing when we increase the step size. Okay, thank you for your time. This was actually a little bit long. I really thank you for your time. Please note that more details are available in the PDF, which can be accessed at this link that is available at the end of this video. Again, thank you for your time, and well, thank you.